So let's talk about a mathematical idea that started way back in the 18th century, but has quietly become one of the most essential tools for modern AI. It's called optimal transport. Now, that might sound a little intimidating, but at its heart, it's really all about solving a surprisingly simple and fundamental problem.
Okay, picture this. You're on a beach, you have a big pile of sand, and you want to build an awesome sandcastle. Now, you want to move every single grain of sand from where it is now to its perfect spot in the castle using the least amount of total effort. How would you do it? This simple question, well, that's the core of optimal transport. It's all about moving a distribution of stuff from one shape to another as efficiently as you possibly can.
But of course, this isn't just about sandcastles. When you zoom out, optimal transport is really the ultimate matching problem. It gives us a framework for finding the absolute best way to connect two different sets of things. That could be piles of dirt, sure, but it could also be the pixels in an image or even abstract ideas floating around inside an AI model. So here's the more official definition for you. Optimal transport is a way to compare two different distributions by figuring out the minimum cost it takes to turn one into the other. And that word cost is absolutely key here. It could mean physical distance, sure, but it could also be energy or time. Really, whatever precious resource it is that you're trying to save. The story of who first tried to solve this formally is pretty cool. It takes us back to the 1780s, to a French mathematician named Gaspard Monge. And his job was actually a very practical one. Figure out the most efficient way to move massive amounts of soil to build fortifications. He came up with a really elegant plan, but as we'll see, it was flawed. Monge's idea was what you'd call a strict one-to-one mapping. Think of it like pairing up dance partners at a ball. Every single grain of sand in the starting pile has to go to exactly one unique spot in the final sandcastle. You can't split a grain of sand, and you can't leave any destination spot empty. It's this perfect, clean, but very, very rigid assignment. And here's where this beautiful idea just hits a brick wall in the real world. What happens if your starting pile of sand and your final castle don't have the exact same amount of sand? What if you need to take one scoop of sand and spread it across two different towers? Monge's plan? Well, it just breaks. It has absolutely no answer for situations like these. So let's just lay out Monge's plan here. It's rigid. It demands a perfect one-to-one match. And it completely fails if the masses, the amount of stuff, aren't equal. It just cannot handle a situation where one source has to split and go to multiple destinations. And for nearly 200 years, this limitation was a major, major roadblock. Then, fast forward to the 1940s. A Soviet mathematician named Leonid Kantorovich comes along and has a revolutionary breakthrough. Fun fact, he was actually working on problems related to planning for the Soviet economy, and in the process, he figured out how to make this old problem universally solvable. And this quote really gets to the heart of the paradigm shift. Kantorovich's genius was to just relax Monge's super strict rules. Instead of this deterministic one-to-one plan, he said, hey, let's think about this in a more flexible, probabilistic, kind of fuzzy way. This new, brilliant concept is called a transport plan, or a coupling. It's not a simple pairing anymore. Instead, it's a much more sophisticated plan that describes, what percentage of stuff from each starting point should go to each destination point. And this right here is the magic trick. This is the core innovation, mass splitting. A single point in your source can now supply multiple points in your target. This one simple change makes all the difference in the world. So now we can finally complete our little comparison. Where Monge's idea was rigid, Kantorovich's is flexible. Where Monge demanded equal mass, Kantorovich can handle totally unequal amounts. And this is the big one. Where Monge's problem might not even have a solution, Kantorovich's formulation always finds the best possible plan. It was a complete and total game changer. Okay, so this new, always solvable framework, it gives us something incredibly powerful. It's much more than just a plan for moving things around. It's actually a really profound way to measure the distance between two different sets of data. This minimum cost, the actual solution to Kantorovich's problem, has a name. It's called the Wasserstein distance. You'll also hear it called the Earth Mover's distance, which is just a perfect intuitive name for it, right? And what makes it so special is that it acts as a true common sense measure of distance between two distributions. But hang on, Why is having a true distance so important? I mean, what makes this Wasserstein distance so much better than other, simpler ways of comparing two data sets? All right, let's break this down. A simpler metric might look at two different data points and just say, yep, they're 100% different, end of story. It's a binary yes or no answer that completely ignores how close or how far apart those points actually are in space. The Wasserstein metric is so much smarter. It gets the geometry. It knows that 2 points right next to each other are way more similar than 2 points on opposite sides of the universe. It doesn't just ask, are they different? It asks, okay, how different are they, and what's the actual work required to bridge that gap? And this unique ability, this power to understand and put a number on geometric distance, is precisely why this centuries-old mathematical theory is now right at the heart of the AI revolution. I mean, think about it. Being able to measure a truly meaningful geometric distance between really complex things, like the layout of pixels in an AI-generated image versus a real photo, or the arrangement of words in two different sentences, that is a genuine superpower for machine learning. It gives these algorithms a much more nuanced, intelligent way to learn and get better. And trust me, it is everywhere. Optimal transport is a key ingredient in training generative adversarial networks, GANs. It's fundamental to the diffusion models that are creating all that incredible AI art we see online. Researchers even use it to peek inside and better understand the inner workings of massive language models. From the absolute cutting edge of AI research all the way to practical things like automatically balancing the colors in a photograph, optimal transport is the powerful engine humming away behind the scenes. Just think about that journey for a second. A practical problem about moving soil for French fortifications has given us a tool to literally measure the distance between abstract ideas. It's the perfect example of how fundamental math can unlock revolutionary technologies centuries later. And it leaves us with this huge, fascinating question. Now that we have this powerful ruler for measuring the difference between complex concepts, what's the next frontier we'll be able to explore?